Atomics, and he's here to talk about nuclear fusion and related topics. So give a round of applause to Andrew.
All right. So good afternoon, everyone. I'm about to do one of my favorite things, which is talk to people who are way smarter than me. So let's go ahead and begin. So I work for General Atomics. This is actually an image of General Atomics right here. This is an older image. This area right here, if this image were taken today, would be the UCSD track. So this is just sort of to give you an idea of how close we are to this right now. When the campus was designed, this center here was designed to sort of represent the atomic nucleus, and this outer building is the electron ring, I guess. Wow, this is really tall. Okay, so General Atomics. This is another view of the campus. Again, there's the Pacific Ocean. UCSD would be somewhere over here. General Atomics was founded in 1955 by General Dynamics. It is in San Diego, as I just mentioned. Today, it is a separate company. It's not part of General Dynamics, and it's actually owned by two brothers, so it's a privately held company. High-tech research, design, manufacturing, and production for industry and government worldwide. And the original mission statement of General Atomics was that General Atomics was founded for the purpose of harnessing the power of nuclear technologies for the benefit of mankind. So a little bit earlier, why did someone decide to make a company like General Atomics? In 1952, Eisenhower started the Atoms for Peace program. He opened up the atomic secrets to the world for peaceful uses. Up until this time, of course, the atomic secrets were military secrets, and obviously had only been used not for peace, but for war in 1945. Obviously, everyone knows that. And Eisenhower actually stood in front of the United Nations and said, "The United States pledges before you, and therefore before the world, its determination to help solve the fearful atomic dilemma, to devote its entire heart and mind to find a way by which the miraculous inventiveness of man shall not be dedicated to his death, but consecrated to his life." And to me, this, even though this was said in 1952, this sort of still holds true to me today. And it's hard for me to imagine a current world leader getting up in front of the United Nations and saying something similar. I like to imagine, what if this instead of fearful atomic dilemma said global worldwide ecological catastrophe? It's very hard for me to imagine a world leader saying that today. Okay, so here's sort of some of the products and technologies that General Atomics works on. Here we have magnetic levitation train. Maglev train would not actually go faster or anything like that, but it uses about 1/3 to 2/3 less fuel than a conventional train. And it actually magnetically levitates using the Lorentz force off the track. And it's sort of like you're riding on a cushion of air, I guess. And we actually have a short maglev track here in the Serno Valley, again, very close to where we are right now. Electromagnetic systems. This particular image is of it's called EMALS, Electromagnetic Aircraft Launch System. This is a system that is there already is a stationary one on an airfield. This is to replace the catapult that launches the fighters off an aircraft carrier. The current technology is steam technology, and this is, again, an improvement, and all future aircraft carriers will have it. It's being installed on the Gerald Ford. Britain would also wants to use it as well. And it allows you to really throttle the energy that you're putting into it, as opposed to a steam valve, which is either on or off. And I'm not going to talk, I'm sort of just going to go over these quickly, and then we'll sort of get into what I work on. So the most famous product that we work on is the Predator drone. That's probably the closest thing that we have to a household name product. We work on sensors for aircraft in general. So this is synaptic aptitude radar, which it actually takes different scans of an object as it passes over it and compiles a composite image. So this is how you can see through trees, see a radar image through trees, through leaves of trees, and so on. Demilitarization. So we work. This is a process that we have called cryofracture, where we take munitions, anything from an artillery shell down to a hand grenade or a bullet, and we actually freeze it so cold that it cracks open. And then you can take the chemical explosive out of it and burn and sort of portion it out, and can be burned. It can actually be used for energy. TRIGA. This is TRIGA stands for Training Research Isotopes and General Atomics. TRIGA is one of our first products. This is a research reactor. It's inherently safe. There are over 70 of these built. We're still building them today. And it's so safe that undergraduates use it. That's how safe it is. And it actually does glow blue from the Cherenkov radiation. Controlled fusion. This is inside of D3D. This is sort of what I'm going to be talking about today. This is some more of the reconnaissance. Railway maintenance vehicles, again, Predator drone, also some optics on that. I believe this is part of the cryofracture. Cryotech de-icers, we don't really use these a lot in San Diego, but in Boston, where I'm from, you know, if it's cold out, they hose down your plane with chemicals to make it safer to take off. Next generation nuclear reactors, this would be a next generation fission reactor. There haven't been any fission reactors built in the United States since 1977, 3 Mile Island, of course, but this is an inherently safe next generation pebble bed reactor. Biofuels, I'll be talking a little bit more about that. This is one of our algae ponds here in Serrano Valley, and we also work with uranium mining. Just a couple more things here. This is that atomic nucleus that's the center of campus, as I pointed out before. I don't know, it's an interesting anecdote. I recently found out in the 80s there was a movie called Real Geniuses, and Val Kilmer was on campus filming scenes. I just thought that was kind of interesting. This is a giant mining truck. You can see this is an SUV. Look at how big that is. I would stand about that tall on that thing. Those are really interesting. This is electromagnetic railgun. So this is similar, sort of similar to the maglev. This is a gun it's called Blitzer. It uses no chemical propellant. It just uses pure energy, electricity, and it's more powerful than any gun, any conventional gun. This product is called Grids. This is a soluble lead flow battery. This is actually an ARPA-E award-winning project. This would be something that you would put in like a solar power plant to store the energy during the day and then slowly release it during the night. And this is the fission reactor on a truck bed. So I think I already talked about most of these. Aircraft launch, algae, railgun. Hybrid electric drive. So we all know about hybrid cars. One of the projects that we work on is actually converting the entire U.S. destroyer fleet to basically hybrid vehicles. So they would be just like a hybrid car to save energy. We do a lot of power conversion, energy storage, things of that nature, maglev, fission, magnetic fusion. Inertial fusion, so inertial fusion is when you have a fuel pellet that you bombard with lasers, and the pellet actually has to be a perfect sphere. We make the pellets for this. The pellets are called targets. The targets are actually so close to a sphere that if you were to have a very high-powered microscope and look at the sphere, the hills and valleys of it would only be 6 atoms up or down. And when you bombard it with the lasers, the energy all compresses inwards, and there's so much that fusion happens. So magnetic fusion, inertial fusion. The third type of fusion, of course, is gravitational fusion. Gravitational fusion is the way that the sun and the stars work. The difference between a planet and a star is after a certain point, after it gets to a certain mass, the center of that planet gets squeezed so much and gets so hot that ignition happens and the entire planet turns into a star, and that's fusion. Hazardous waste, email, energy storage, high-powered lasers, we sort of already talked about all of those. This was also one of General Atomics' first project. I just think that this one is pretty cool. This was a top secret project, was not even known that we were working on it until the 80s. The lead on this was a famous physicist called Freeman Dyson. I don't know if anyone's heard of him. He's still alive today. And this is a spaceship. And the design is it operates through means of exploding nuclear charges, pulse units to impart motion derived and detonated at 1 to 10 second intervals. So this spaceship would have a lot of little atomic bombs on it, and they would basically, this is the gun right about there, they would shoot out the back, explode in space, and the inertia would cause the spaceship to be propelled forward. I think it's kind of cool, but obviously it's limited nuclear test ban treaty hindering design. There's not any atomic weapons allowed in outer space due to this treaty, so, and may be a good thing at the end that we didn't build it. But this particular ship has been proven to be scientifically feasible, and it's believed that this could get up to about 10% of the speed of light. So the speed of light is the universal speed limit. So it's pretty interesting to me that human beings already have the science to get 10% there. So, why do we need new sources of energy? This is sort of, now we're moving into the energy stuff. This is sort of why we're all here. I think everyone knows what this graph means, has seen similar things before. We all know that the supply and demand of fossil fuels will come to a certain point where we can no longer, we won't run out of fossil fuels necessarily, but we will come to a point where we can no longer meet the rising demand. Some people call this peak oil. And obviously there needs to be new sources of energy supplied to make up the difference. And this is engineers for a sustainable world. So we all know that by if you reduce, reuse, recycle, we can push this out. And hopefully we can push this out a long way. But it's not going to be possible to continue using fossil fuels forever. This point will come, and it's possible that it will come in our lifetimes. We obviously don't know. So how are we going to solve this? So this is one of General Atomics' projects, plastic waste to energy. We all know that plastic is a petroleum product, and this is sort of that idea of reusing. You can reclaim the entire energy content of the plastic waste by basically converting it back into gasoline. And that's exactly what we've built, an engine that does that. It reclaims the entire energy content, reduces supply chain energy use, reduces landfill use. It's obviously not, this one is obviously not a perfect system. It's still fossil fuels, but again, how do we push that line on the graph I just showed you further? Advanced chemical and biological processes. This is General Atomics algae farm in Kauai. I've actually been there. This is our smaller algae farm in Sereno Valley. This is one of the algae. So green algae can be grown in brackish water. It doesn't influence the food prices, and it can be grown on arid land. So places like Brazil have great biofuels programs. They use corn, for example. Now, when you use something like that, the global price of food always goes up. So that's one of the disadvantages. And actually, even if you were to convert all of the United States farmland today and turn all that biomass into fuel, that would not be enough fuel for the United States, even if we converted every single piece of farmland. So that's why we have to choose something different. And you can use brackish water. It can basically be grown in the middle of the desert. It's a carbon neutral process. Again, this is not a perfect energy source, but the carbon, the CO2 emissions that come from it were absorbed from the atmosphere in the first place while the algae were growing. The algae take in nutrients, sunlight, and carbon, obviously, photosynthesis. The algae get fat. We basically overfeed them. We give them everything that they like, and they produce lots of lipids. Fat is also known as a lipid, which is also known as oil. So when you burn it for oil, the energy produces carbon, but no more than was captured from the atmosphere in the first place. So again, reduce, reuse, recycle. This is something that would at least be a neutral process, although certainly not a perfect energy source. This is the small algae pond in Sereno Valley. Again, this is very close to where we are right now. And it's sort of, I guess, once someone told me it's kind of obvious. You start in the small ones, you put them in the middle ones, put them in the bigger one, and get them to the biggest one. You can see there's paddle wheels, and this pond actually is slightly slanted as it goes down, so the water slowly sort of recirculates, and then there's a pump here that puts it on the other side. So this is where I work. This is part of my office. EM squared. So this is called the energy multiplier module. So now we're sort of moving into sort of different energy sources that are different than fossil fuels or sort of reduce, reuse, recycle. EM squared, the energy multiplier module, is a device that closes the nuclear fuel cycle. What do I mean by that? So everyone knows that one of the huge disadvantages of fission power is the atomic waste that it produces. What do we do with that atomic waste? Today we just store it. So I think everyone in this room, well, actually I shouldn't speak so soon, but most of the people in this room are young enough that they were born into a world where atomic waste was already here. It's just accumulating. It's never been, there's no known way of getting rid of it. Well, that's actually not true because there is a way to get rid of it. So this is the energy multiplier module. This is a new type of fission reactor. In this reactor, you would put about 30% uranium in, just the normal sort of fuel that a normal fission reactor uses. About 70% would be atomic waste. And this reactor burns very, very, very hot. It burns so hot that the atomic waste is burned. It's, of course, not chemically burned, but it is transmuted into different elements that are not atomic waste. And, of course, this is what the alchemists were trying to do, find the philosopher's stone to convert one element into another. So we actually do that today. And so not only does this get rid of atomic waste, but it produces energy in the meantime. This reactor would only have to be fueled every 30 years. Anyway, and you might be asking, for the smart people in the room, someone might be saying, but wait a minute, you said you're still using uranium to heat it. So it doesn't sound like you solved the atomic waste problem. But of course, what you would do is you would just build a second one, and you would basically keep building these until all the atomic waste on Earth had been converted into energy for us to use for peaceful purposes. And the interesting thing here is there's more energy locked in the current nuclear waste pile than is in the entire world stockpile of fossil fuels. So this isn't just some sort of niche energy market. This could really revolutionize the idea that we're running out of energy and things like that. Reactor only needs to be fueled once every 30 years. I think I said that. So now on to fusion power. This is what I do. I work on the D3D Tokamak National Fusion Facility. So what is fusion? Fusion is the power of the sun and the stars. Fusion power is star power. So all elements heavier than hydrogen were created through stellar nucleosynthesis. Obviously, all the hydrogen in the universe was created during the Big Bang. Everything heavier than that, the atoms in my body, your body, the chair, the entire Earth, the sun, were all created in the supernova in the distant past. Fusion power. Fusion power has been the quest to create a star on Earth. It represents humankind's attempt to put the sun in a box, or in a bottle, as I'll show in a minute. Inside the D3D Tokamak, it gets many times hotter than the center of the sun. Why does it have to be so hot? Well, because the sun is really, really big. The Earth is minuscule compared to the size of the sun, and obviously anything that we could build on the Earth would be many, many, many times smaller than the Earth itself. So that's why it has to be so hot and so dense. So we're essentially creating a very small, very hot, very intense star on the planet Earth. In 1951, Argentina's dictator Juan Perón, I don't know if people in this room remember, there was a movie with Madonna called Evita. There was a song, Don't Cry for Me, Argentina. This was based on real events. This was her husband, I guess. And he prematurely announced solving fusion power on a secret island. And of course, we know that he did not solve fusion power. But it's interesting to know that this has been going on since 1951. All the time I read about, for example, North Korea recently announced that they had solved nuclear fusion. In the 80s, somebody had said that, you know, for like with $100 worth of material in their basement, they had created a cold fusion reactor that would solve all of Earth's energy problems. This is an old story of people coming up with this. Now, fusion may be solved in somebody's garage by some really smart person. It's certainly possible, but considering that Fusion was first essentially discovered, figured out in the 1920s. The greatest minds on Earth have been spending all that time trying to figure it out. The advantages are so great, it doesn't seem that likely to me. And another point is that this is what started the United States fusion program, was the reaction to von Braun's lie that he had invented fusion. In 1952, Edward Teller detonated Ivy Mike. Well, he built the H-bomb, Ivy Mike was detonated, and fusion had been achieved on Earth in the form of the H-bomb. So what are the advantages of fusion as an energy source? The fuel for fusion is deuterium and tritium. Deuterium is an isotope of hydrogen. Hydrogen is the most abundant element in the universe, so if you have to pick a fuel source, you might as well pick the one that's the most abundant in the entire universe. Interstellar space has deuterium. Deuterium exists in the ocean. 1/64,000th of the ocean is deuterium. Anytime anyone in here has ever drank a glass of water, there's deuterium in it, I guarantee it. There's no CO2 emissions from greenhouse gas. So fusion, I'm not going to get into the science too much, but fusion is, of course, taking two lighter elements, combining them, creating them into a heavier element, and energy is released. And this is what a famous scientist said when he said E equals mc squared. It's Einstein's equation, obviously. The fuel resource will last many millions of years. This is sort of one of the real key points to fusion power, is that there are millions of years of deuterium fuel on the Earth. Not just a little bit, but millions of years worth. And as I said, it's the most abundant element in the universe. It's in interstellar space. Asteroids, comets have deuterium on them. They believe that there's deuterium on the moon, other planets. And also deuterium can be created through a normal chemical process involving lithium. So probably everyone's heard of lithium-ion batteries. Probably everyone's laptop in this room has lithium in it, so lithium is also not a rare material. So there are millions of years worth of fusion fuel on the Earth. There's no CO2. There's also no radioactive waste. So this is one of the huge advantages over fission. Fission fits a lot of these too, but fission has that radioactive waste that we already talked about. There will be local activation of structural materials. I'll show you a little bit more about that in a minute, but it would sort of be the thing where you would build a fusion power plant, you would use it for many years. Yes, when you were done, the building itself would be hot, it would be activated, but it's the sort of thing where you close the doors for about 100 years and the building is perfectly fine. This is not true with atomic waste, where we're talking about centuries and millennia of having it on the Earth. This is, and we'll see a little bit more in a second. So here's a graphic to sort of represent, and again, I mean, I think probably everyone knows about this, but it would take 2 million tons of coal to run the average power plant for a year. That's 21,000 railroad cars. If we look here, you can tell that there's not 21,000 on this image, so this would go far, far, far off the edge of this image here. Oil is a little bit better, only 1,300,000. Again, it would stretch off the map. So fission is a very powerful and useful energy source. And that one only takes 1 railroad car. But fusion, this is sort of why fusion is the perfect energy source. 1 pickup truck of deuterium can run an entire power plant for a year. I mean, so we usually talk about it's a factor of 1 million. So atomic energy is always going to be 1 million times more powerful than conventional fossil fuels and the like. So here is the D3D tokamak. This is what I work on. D3D tokamak was built in the 80s. This, what you're looking at right here, this is actually the vacuum chamber. This is sort of the center of the machine, the main part of the machine, if you will. The whole machine takes up more than a city block. This is not the whole thing. There are other parts that provide the heat and the energy to heat the plasma in the first place. And the plasma is, the fusion plasma inside is sort of akin to the match when you're at a campfire. When you're at a campfire, you have to strike the match, put the match in your fuel, which is wood, and if you did a good job, when you pull the match away, the fire is still burning. So basically, D3D achieves the match part and putting the match into the fire, and the part that D3D does not quite accomplish is the part where you take the match out and it keeps burning. Oh, I'll talk a little bit more about that in a second. So this is called a tokamak. This is a torus. This is a donut-shaped vacuum chamber. That's all a torus means. And this is the magnetic bottle containing a star on Earth. So this, right inside here, this is where it gets 7 times hotter than the center of the sun. How do you build something? What kind of bottle are you going to put a sun in? What kind of box can you put it in? Obviously, any material that you would build it out of would melt from the intense heat. So that's why we call it the magnetic bottle. This is not the bottle. This thing is not the actual bottle itself. The bottle is an invisible magnetic bottle. You can't see it with the naked eye, you can't touch it, but it really is there, it's really measurable. It's a magnetic bottle that squeezes and contains the plasma inside. This is the inside of D3D. So as you can see, what we're talking about, local activation of structure. This person is not wearing a radiation suit. They're wearing a clean suit, but they're inside. Yes, it's more radioactive in here, in this room, than it is in this room that we're all in right now. But it's not so much that a human being can't enter in unaided for short periods of time. You wouldn't want to have your desk in here or anything like that. But you can see, this is sort of a good image because you can see the different diagnostics. There are over 70 diagnostics on D3D. Diagnostics are sensors, probes, things like that. And when D3D first started in the 80s, there were 0. So one of the great accomplishments that we've been able to do is study the plasma greater and greater, be able to look at it. And the next step, and this is some of the stuff that I work on, is being able to simulate it. If you know enough about it, you can just run it inside a computer. You don't have to actually build the thing. So what are we talking about? Why is fusion important? Again, so this is my nutshell slide. So here's the nutshell, right? The point is to heat water, make steam, turn a turbine, turn an electrical generator, and make electricity. This is the way that pretty much every power plant on Earth works anyway. The only difference is here, for the heat source, this would normally be coal or oil or something like that. Here, it's a star, a sun on Earth. And it's also interesting to note that, I guess, I was trying to think about it earlier, maybe geothermal or something doesn't quite count, but almost every energy source that we have today really is one step removed from fusion. Everyone knows that fossil fuels are dead plants and animals. Where did the animals get their energy source from? Plants. Where does plants get their energy source from? The sun through photosynthesis. And the sun is a gravitational fusion reactor in the sky. Wind turbines, what makes the wind blow? It's the heat of the sun, fusion power again. Solar energy, obviously, is just collecting the energy from the sun 8 light minutes away on Earth, the tiny fraction that hits us, and then hits the solar collectors. This is a cross-section of D3D, so here you can see, this is an older slide, but here you can see some of the diagnostics. This green thing is a giant copper electromagnet, and that's what creates the magnetic field, that the magnetic bottle that holds the fusion plasma in place. You can see that there are a number of diagnostics here that scan through. So one of the interesting developments, there are new tokamaks in China and Korea. They're basically copies of D3D. We built it from scratch. They basically took what we had and copied it. But the real advances that they've been able to make are using superconducting magnets instead of copper magnets. So our copper magnet gets really, really, really hot. D3D actually only works for about 5 seconds, so it can only sort of maintain and contain that plasma for 5 seconds. The Korean and Chinese tokamaks have done a little bit better. And here is the ITER project. The ITER project is the culmination of all the fusion science that has basically ever happened that human beings have ever figured out. The ITER project is a large tokamak that's being built in France right now. It's an international project, that's why it's called ITER. It would have been built in the United States, but the United States actually chose to not take a leadership role, and Europe had to take it on then. ITER stands for International, well, it used to stand for International Thermonuclear Experimental Reactor. It's now just called ITER. I guess some people didn't like the thermonuclear part of it. It scared some people away. So this is well, the goal of this project is to create Q greater than or equal to 10. The scientific goal is to deliver 10 times the amount of power than it consumes. So right now, D3D, the tokamak that I work on, when it's on, it consumes about 20% of the energy that San Diego provides. It takes a lot of energy to have those magnets, create the magnetic field, heat the plasma, and maintain it. So we have to put a lot of energy in. Remember, that's like the match. That's sort of putting the match to the logs of wood. But we don't, when we turn it all off, it's not a self-contained fusion process. So we produce energy, but we produce a little bit less energy than we put in the first place. And we all know, there's no perpetual motion machine. You can't build a power plant doing that. But ITER, when you scale this up and use the new technologies such as the superconducting magnets that I mentioned before, it is achievable. And of course, we know that it happened. And part of the whole fusion experiment is, how do we know that this works? Are we just chasing after something that will never work? All we have to do is look up in the sky, and we see time and time again, there are literally billions of fusion reactors in the sky for us to look at any moment. Taxes of 34 nations pay for ITER, including the United States. What I find fascinating about this project is, when was the last time that 34 nations did anything together? We work with some of the major contributors. Oh, well, of course, European Union is one of the member states. We know that European Union recently won the Nobel Peace Prize, which of course was because they have sort of quelled the two adversaries of France and Germany. There hasn't been a war in Europe for about 70 years. Before that, there was 3 wars between France and Germany in the 70 years before that. Russia, United States, obviously were adversaries for a long time. We now work together on this. And actually the beginning of ITER was right around the time, I guess to date myself, right around the time I was born. Ronald Reagan and Gorbachev met, and one of the things they talked about was working on a fusion reactor. And today, we're building that fusion reactor. More than half the world's population are united to peacefully study fusion and to create a fusion power plant for everyday electricity. China, India, United States, Russia, European Union, huge population centers. Those are all nations on the project. So, I guess the theme of the conference was, what's our legacy? Realizing a sustainable future. So, I just had basically 2 slides here. The first 2 quotes are actually, I guess they're made up. I guess most people didn't really say those things, but I put them on here anyway. Why did people even think that this was said? Why are people still misquoting these people? Thomas Watson, he should be prominent in people's mind recently. The Watson supercomputer won on Jeopardy. It's named after this guy. I think there's a world market for maybe 5 computers. Obviously, we know that this didn't come true. There's sort of this famous quote that, again, we don't really think that he actually said it, but supposedly in 1899, he suggested that everything that can be invented has been invented, so the US should close the patent office. It's really these sort of lack of foresights in science that I always find interesting. This next one, Thomas Edison, obviously a very smart person, got a lot of things right, but he said in 1895, 7 years before Kitty Hawk. It's apparent to me that the possibilities of the aeroplane, which 2 or 3 years ago were thought to hold the solution to the flying machine problem, have been exhausted, and that we must turn elsewhere. Again, he was wrong. You had every reason to believe this person. He was an expert. But we've also learned, of course, through history that the opinion of experts is not always going to reflect reality. I just like this one. I thought this one was really funny the first time I read it. That rail travel at high speeds is not possible because passengers unable to breathe would die of asphyxia. It's just so amusing to me that, and when he's talking about high speed, he's talking about like 25 or 45 miles. So, obviously a simple test could have proved this wrong. And the one I didn't put on here would be at the end. Would be, I mean, we're here. This is Engineers for a Sustainable World. The last item that would be on here would be, there is no global environmental change. Carbon emissions do not influence climate. There's certainly some contention about how much it does. Some people argue, well, we don't know if the humans are doing it or not, but just because someone else is causing a problem doesn't mean you ignore it for anything. So that's sort of the point that I'm trying to get with this, is that there have always been, I didn't put this, but I call these basically the naysayers of science. There have always been people saying that things were wrong. But some people sort of have got it right. Some people have had the foresight. So here we have Seneca the Younger, circa 30 AD, about 2,000 years ago. He said, many things that are unknown to us, the people of a coming age will know. Many discoveries are reserved for ages still to come. Nature does not reveal her mysteries once and for all. And when I read this, I don't think that, so we saw some people who got it right, some people who got it wrong. I don't think that this is just a coincidence that he said this. I don't think that, if you look through a historical text, I'm sure you can find anything to support anything. But this sort of goes to this point. History has shown that we tend to underestimate ourselves. And we tend to sometimes think that incredible problems like sending a man to the moon, curing a disease like smallpox, or even flying in planes, even riding on a railroad, people have said it's impossible. Go study something else. I put Robert Goddard on here. Robert Goddard is the father of modern rocketry. Obviously, the Chinese invented rockets much before that. But one of the reasons I put him on here is because he is a Massachusetts man like myself. It's difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow. And again, there was actually a New York Times, again, so we have to look at the opinions from the experts. There was a New York Times article in the 20s that said that a rocket cannot fly in space, and it went on and on and on and said that a rocket cannot leave the atmosphere as soon as there's no oxygen, you could never fly a rocket. And actually, in 1969, during the moon landings, they, whatever it was, 49 years later, published an apology and said, clearly we were wrong. So we do not know the limits of our ability to solve problems. History shows that we tend to underestimate ourselves. We look around today, we have devices that fit in our pockets that are more powerful than any computer in the past. I read that the these greeting cards that you open that play a sound, these cards have more computing power than the entire Allies had during World War II, and yet we just throw it into the trash. So it's phenomenal, the advances of science, and we don't know what our limits are. Greatest accomplishments of humankind were impossible. Really quick, I always find it amusing when people think that Stonehenge or pyramids or something had to be created by aliens because human beings could never do it. I mean, obviously we've proven we can do lots of things. Anyway, so our legacy, what is our legacy? Our legacy will be reducing human drudgery, creating and engineering solutions to better the lives of everyone and for all time. And that's actually all the slides I had. We have about 5 minutes left. I'll open the floor up for questions. I'll do the best to answer them.
What are the main technological advances that make you optimistic about
Well, some of the major things definitely are the superconducting magnets. And also one of the things that people predict in the future is that there'll be actually room temperature superconducting magnets. The ones on ITER have to be super cooled, but we do believe that in the future we'll be able to create room temperature ones, which will make the problem even easier. We also know that as we scale up, essentially ITER is similar to D3D, but it's a scaled up version. And as we've seen, that the problem gets easier to tackle with the larger size. So actually, I'm going to go back because I forgot to show the picture of the human. There's the little human right there. So this is really, really big machine. And if we go back to D3D, well, there you go. There's the human. So it's about 4 times bigger. So those are some of the reasons. Thank you.
I know you said about new nuclear waste process where you essentially burn it. Can you explain that just a little bit more?
Yeah, so in fusion, which is what happens in the tokamak, it actually transmutes metals. So when you get something so hot, it turns into a plasma. Remember, that strips the, remember there's 4 states of mass: solid, liquid, gas, plasma. When you get up to a plasma, you actually have the protons, neutrons, and electrons all just sort of spinning around independently. So the idea here is that if you get the nuclear waste so hot that it becomes a plasma, that when it cools down, it doesn't recombine into the nuclear waste. But you have to be really, really, really hot. Those reactors run, I believe, about 4 times hotter than a conventional nuclear reactor. And I mean, there was a Superman movie where he throws the nuclear weapons of the world into the sun. I mean, anything will melt, anything can be transmuted into different metals. And that's sort of what we do there. That's right. So that's why we call, I'll go back to it, that's why we call it closing the fuel cycle. So in a conventional atomic reactor, the fuel rods can be used for about 3 months. At the end of the 3 months, a small percentage of that has turned into nuclear waste. The rods have to be taken out and what's known as reprocessed, where they take the bad stuff out, put the good stuff back together and use it again. So this closes that cycle and when they take those parts out, we have no idea what to do with them. We just store them in barrels. And yeah, maybe you can store them really securely, but obviously they're still there, and they're going to be around for a long, long, long time. So.
You said that lithium and hydrogen, that we have plenty of them, so that's not a problem. But isn't most of the hydrogen, I mean, it's the most abundant element, but it's most of it like in water. It's not in elemental hydrogen. So does that really solve the problem? Because then we have to put in energy to get hydrogen from the water. Yes,
that is true. But you get far more energy out than you get through the process of splitting the water into the hydrogen and oxygen. So it is true that you need, and like I said, you need to put energy in. You need to have that match. So the first, so when we run our fusion power plant, we're running it on conventional energy. So it is true that you sort of have to start getting some fusion power plants, but the energy from the fusion power could be used to separate the deuterium out of the water in the future. Good question, thank you.
Is the answer compatible with thorium?
I believe thorium is one of the waste products that this uses. Yeah, I believe so, yes. We have 1 more minute.
How close is the specific project to being used?
That's a great question. So Basically the design is complete, it's been scientifically validated. The real problem here is that there has not been any nuclear power plants built in the United States since 1977. Nuclear power plants run well every single day. Obviously there are dangers, and there have been a few bad apples, Chernobyl, 3 Mile Island, Fukushima recently. I mean, I'm optimistic, I guess, because I'm an optimistic person, but I don't know how likely it is that the government would be producing new reactors right now. So basically, the answer to your question is there are political barriers, and those are the main barriers, not scientific.
I know Bill Gates did invested in some manufacturing company, but that company is actually going over to Europe. There's a European country that's allowing them to test new nuclear reactors there. Is that like a feasible option for you guys? Is that what you are thinking of doing?
Well, we would obviously like to do it in the United States, but yes, so for example, TRIGA, which is the research fission reactor that I showed earlier, those aren't being still built in the United States, but places like Morocco and other countries, they're the sort of countries that are looking to advance this technology. And sort of like I said with ITER, is the U.S. everyone in the world wanted the U.S. to take the leadership role, but it chose not to. So there's a lot of political issues.
Also, I thought there was a nuclear reactor going into Georgia.
Yes, you may be right, but essentially, maybe with an exception, there have not been any. There have been certainly no large-scale nuclear facilities or projects in the United States. So I think I'm out of time, actually, so thanks so much.
Oh yeah, you got this. I'm like doing your stuff.
What do you need me to do?
You have a flash drive, right? Yeah.